here is a cost function. Cost, least amount of money necessary to make output Q, as usual, given that emissions will be E. So I just added a term. What you'd expect is as you are allowed to emit more, your costs will either go down or at least not up, or as you're forced to abate, your costs will go up. So C ought to be decreasing in E. Costs go down, emissions go up, and that gives us marginal cost of abatement. If we had, because it's abatement, if we had one less unit of emissions, what would happen to our costs? So here's our cost with one less unit. Here's our original costs. With one less unit, this is going to be a bigger number, right? I took away a unit of emissions. Marginal cost will now be up, and so this will be defined as a positive number. How much it would cost you if you had to emit 1 unit less. That's marginal cost of abatement. And here's one of our pictures again. You've seen this one. Originally, firm chooses to produce at 24 and whatever that is, and 2050. Yeah, we still have a price of 2 for other stuff. This is example. Oh, there it is down there. I'm hiding it. Price of 2 for other stuff. So this is the original isocost line. It hits at 80. 80 times 2 is 160 is the original price. I forced them to abate how many units? 4 units. I'm going from 24 to 20. Abate 4 units. How much do their costs go up? Their costs go up from 160 to 180. And so I can calculate out an approximation of the marginal cost of abatement by a little quick division. I guess I get 5. So it costs $5 per unit to abate. And that's an estimate of the marginal cost of abatement in that diagram. Well, it's a cost, so it's got to be in dollars. And it's, you have to, it says air. So perhaps this is in tons of NOx. Right? So it's $5 a ton of NOx. Yeah, but it's got to be some physical unit. Dollars per physical. Absolutely. E is emissions. Emissions are some physical thing. So one day I should put units on that. Now in this next little piece, I'm going to try to convince you that the amount that that a firm would be willing to pay for the right to emit 1 more unit is the marginal cost of abatement. Logically, that makes sense. Look, if I get to and maybe I can do it better than it's on the slides. Maybe that's what we'll try it this way. I get to emit 1 more unit. Yeah. Therefore, my costs go down by exactly marginal cost of abatement. That's the savings I get because I can emit 1 more unit. But what else happens? I might make a little more output. If I made a little more output because I can emit a little more, what would I get paid for the output? P per unit. Agreed? And what would it cost me to make the additional unit? What does it cost to make an additional unit? There's a name for that. Come on. We're reviewing for our test here. Marginal cost, right? So you just argued that if you want to know how much the profits change, I'm writing on the board, but it's on the next slide. Oh, let's take up the slide and I'll write on the board at the same time. So if I look at the top line, profits, price times quantity minus quantity, cost of quantity, right? And what I want here is I want the change in profits if I can emit 1 more unit. That's what I want. And I'm going to argue that you'd expect, of course, that marginal cost would change. I can emit 1 more unit, so I'd make some more output. Yeah, that would make sense, would it not? I can emit more, so my marginal costs of production are lower. That's the argument. You make a little more output. And then here I do a fair bit of algebra to just find out what is the difference between profits with 1 more unit and profits. And I think I can do that faster this way. So what could happen? I can emit 1 more unit. Certainly, it costs me less to produce. By how much? By the marginal cost of abatement. Right? That's what it costs me. But I might make additional units. We'll just call them add units. I don't know how many there'll be. And for each additional unit, what do I get paid? What do you get paid when you sell something? Price. And what would it cost me to make the additional unit? And what does price equal? Okay? That has a name in economics. That's called the envelope theorem. And here I do it out in detail. And those of you who know the calculus well will notice that this approximation right here works in the calculus. So if 1 is very, very small relative to E, this approximation will work. And then you get algebra that does exactly what I wrote on the board. If you do it in the calculus, it'll work much faster. You want to do it in the calculus? It's really fast. Yeah. Profits equal, right? Price times quantity, which is a function of E, yeah, minus cost, which is a function of quantity, which is a function of E and E. And I want to make E go up a little bit. I take the derivative. And what will I get? I'll get price times dq dE minus marginal cost, which is the derivative with respect to Q, right? Times dq dE minus, or plus marginal cost of abatement, which is, of course, minus. You want to be accurate about it. Yeah. And P minus MC is 0. And there you have a type proof in 1 line. And that's why you want to learn the calculus, because it takes 2 pages of discrete approximation that you can't follow to do it. You can do it in 1 line in the calculus. Okay, my rant is done. So what we need out of this is what a firm is willing to pay for another unit of pollution. Here we just go all the way down to bid equals, is the marginal cost of abatement. That's what a firm's willing to pay for the right to pollute 1 more unit, 1 more ton of NOx. Most textbooks will start right here. They won't have done what we just did. And they'll just say, look, so here's what a firm's willing to bid for tons of emitted NOx. If they're getting to emit nearly 0 NOx, then it's really valuable to them, and they'll bid a lot. Well, that makes sense. And somewhere out here, the right to emit is worth near nothing. If you take coal and you burn it, there's only so much NOx you can make out of it and still make anything else. So the price really does come down. Well, you can think about what this would mean in a coal-fired power plant. Somewhere down here where you hit 0, What's that? That's I run my coal-fired power plant and I basically maximize the heat rate. I don't care about anything else. What do you do to take the NOx back a little bit? You burn the thing a little bit cooler. Just the flame down a little bit. You don't have as much thermal efficiency, but you don't have as much NOx either. And so there's some cost to doing that. You lose your thermal efficiency. As you come back in here, you're starting to do things like crush and wash your coal to get out some of the impurities. And way up in here somewhere, you're building a selective catalytic reduction unit, which is itself bigger than the coal-fired power plant. So when you say, look at a modern plant, and you look at the pollution control equipment, you'll see the pollution control equipment is a superstructure around the original plant and is bigger than the original plant and might actually cost more, like hundreds of millions of dollars. So cutting back tons of emission means you're picking up different technologies to do it, taking the first ones being cheap. But when we get back in here where we are today, these things are expensive. Yeah. So that's the marginal cost of abatement curve, which is also, or that's the bid curve for tons emitted. And if you take the same curve and do it in abatement space, you get exactly the same story. This is no abatement, right? So it would start off at some base level, unknown. It's no abatement. And here you are adding various technologies to get the air cleaner, meaning you're doing more abatement, and the costs go up as you add. So the more you abate, the more it costs. Trading lowers total cost. This was your trading game. We do it in a two-headed diagram. So the idea is there's a fixed number of tons emitted, and there are two firms. And I'm going to read one firm this way. And so as I come out here, it just says the usual axis. The other firm I'm going to read backwards. As I come this way, it's more and more emissions. And when the two arrows meet like this, I use up the total. So I've written it here as if it's almost half and half. But this arrow could be shrunk and this arrow could be longer. So long as they meet, they use up the total emissions. The question is, where should they meet? What's the right idea? What's the right answer? It's useful to go back and ask about the area under the marginal cost. Here it's emissions. So the area under a marginal cost curve is a cost curve. Same argument as always. How much would it cost me for the first 10 units, the blue box, the next 10 units, the purple box? So what would it cost for 20 units, the blue plus the purple? Area under is the costs, the avoided costs here for tons emitted. Now I've drawn two firms. Here's tons emitted, and here's their bids. If you had almost all, if you're over here, that means firm 1 emits nearly nothing, right? And firm 2 emits what's left, a lot. Come here, this is a 50-50 split. Come over here, there's the magic point where we should be. And when you get all the way out here, firm 1's doing all the emissions and firm 2's doing none. So that's the bids I've set down for two firms. And you notice I set them down so that the two firms aren't identical. One of these firms is better at cleaning up than the other. This firm is willing to pay a huge amount for a little more emissions. This firm doesn't change what it's willing to pay per unit of emissions very much at all. So they're very asymmetric firms. So how much are to each? So suppose we gave it evenly. Well, here is firm 1's right, avoided costs, area under the bid curve. That's how much cost they would avoid if they could emit half of all the total emissions. And here's the one for firm 2. And here's some daylight. Well, what happens at this point? This was your game exactly. Here you are. Firm 1 is willing to pay the amount that you can find to look at the corner of the blue box on the red line, right? Big amount. What's firm 2 willing to pay for a unit more of emissions? A smaller amount. So the two of them could trade. They could come this way by 1 unit. And if they do that, firm 1 is going to have big avoided costs, and firm 2 is going to have small additional costs. So any price in between, they'll both make money, and they'll both do it. As you learn from the trading game, there are a lot of prices in between. Did somebody here kill it? Did anybody kill it? Get the biggest amount of money? Yeah? Who just utterly killed it? What? Okay, so you know, how good you are at negotiating matters in life, doesn't it? Yeah. So we don't know how much money is going to get made. We don't know what the price is going to be. We just know it's going to be somewhere in between. Obviously, it could be almost all the way up here or almost all the way down there. You can play the same stunt until you get out to where the valuations are the same. Another way of saying that is that we left money on the table at a 50-50 split. How much money? The red area. The difference between the area under one curve and the other. That's how much money was left on the table. Nobody took it. If only we had somehow shifted out to here, had this guy, Mr. 1, emit a little more, Mr. 2 emit a little less, then the costs in the system would have gone down by the red. And what happens to the amount of pollution? Is it the same? Was it the same in your trading game? Did pollution go up or down? Pollution goes nowhere, right? Yeah, so that's the idea of a cap and trade system. The pollution stays the same, but we make the guys who find it easy to abate do the abating. This guy has very little cost in going from here to here compared to the gains this guy gets from going here to here. How big are these numbers? Well, until relatively recently, there weren't all that good studies. The older studies would tell you that the total cost of achieving clean air is much higher with TDS than it would be without. But it was really hard to know. You're basing it on a very partial study of the cost of cleaning up. And if you look at different states, you get different answers. California would come out very close to efficient. The other states would not. And what I think happened was California had a lot of cleaning up to do and had a very competent air resources board and spent a lot of money figuring out what would be the efficient way to do it, where other states didn't do that. That's what I think happened. We will show you in a minute an example of cars and power plants and how today they're not set up correctly. One of them abates too much and one too little. And then if you wanted to look in the literature, I can find you a nice article that says something like counties that have non-attainment in one or more pollutants under the Clean Air Act grow substantially slower in terms of manufacturing than counties who are in attainment. And they also have higher or lower efficiency in the manufacturing sector. So that would be newer results. And all of these results say the same thing. Free, it's not. So someone tells you, oh, there's this great guy, Michael Porter, and the Porter hypothesis is if you only make them clean up their pollution, then they'll really think about what they're going to do, and not only will they clean up their pollution, but their plant will get more efficient, and their costs will go down. And there's no evidence that I can tell for the Porter hypothesis, although it's a very comforting hypothesis, and we do wish it were true. So that's roughly the state of play and what it costs. Cap and trade we know about. There are many different trades that used to be allowed. At one point, they restricted trade. In the early days, they restricted trade. So they'd allow one plant on one piece of property has 2 smokestacks. And they draw an imaginary bubble over the plant and say, we only care what comes out of the bubble. You can allocate between the 2 smokestacks within your plant. And then they made the thing bigger, and they allowed plants that were near each other and owned by the same firm to do it. But eventually, you got the acid rain provisions of the Clean Air Act, and you were able to trade very broadly. One of the problems with trade is you might trade pollution from a place where it's harmless to a place where it's harmful. And if you look at the California coast, Southern California coast, if you emit on the coast, like the refineries do, then you pollute the people next to you, and then the smog is blown into Riverside where smog goes to die. And so basically you pollute twice. You get all the people on the coast and you get the people in the Inland Empire. Where if you pollute in the Inland Empire, you only pollute one set of people. So you care whether people traded their pollution permits from the Inland Empire to the coast because they'd be doing twice as much damage. And indeed, the actual program for the South Coast, Reclaim, doesn't let you trade 1-to-1. It makes you trade 2-to-1. So if you want to move your pollution back out to the coast, you have to clean up 2 units inland to get 1 unit at the coast. So it's partially taken care of. So trading can put pollution places you don't like, but you can set up your program to really minimize that problem. And real programs, namely Reclaim, do. Now let's go for the right amount of pollution. So here we have optimal pollution. I have millions of tons abated, which is how it's done standardly. Here's my marginal cost of abatement. And this is marginal cost and benefit of SOx abatement. Right? And like you expect with these curves, they're constructed. And so at some point, they take a big cut up. This is where you pretty much know what's going on. This is where you're guessing about what would I do next. And so that's an artifact of how you construct the curves. You ask me what the truth is, maybe. I don't believe quite that. Marginal benefits, there are estimates of what damage is done by a ton of SOx. It's roughly this, 3,000 and some. And the argument is, where do you go? Where marginal cost equals marginal benefit. Same exact idea. Suppose I were at 4. Should I go to 5 units abated? Well, between 4 and 5 units abated, I get benefits of $3,500. I only get costs of about $1,000. And so that's a good idea. The benefits exceed the costs, wildly exceed the costs. And you can keep on doing that until you get to this point where the marginal cost of abatement and the marginal benefit of abatement are the same. By the way, what would be the cost of SOx? Why don't I want this stuff? Oh, there's environmental scientists in here? What's wrong with having SOx in the air? What? Acid rain, yeah, that's one. What else? What? Respiratory problems. And I think that you have to go do your air chemistry, but I think it's the sulfur creates the nucleus for the really small particles. So you want to get rid of the really small particles that get in your lungs. You want to pull down the amount of sulfur. That's probably the big thing. Acid rain is another. All right. So marginal cost of abatement, marginal benefit, right, has something to do with how many people you're going to kill and how many buildings you're going to melt as you have more and more SOx in the air. Now we get to Mr. Coase. Let me tell a story, and then I'll do Mr. Coase. So Ronald Coase lived to about 101. Got it right, he's finally dead, I think. Won the Nobel Prize. Well, he was still giving interviews in his late 90s. If you Google Ronald Coase, you can find interviews with the guy. He's a very interesting guy. He starts off being a little on the red side, which would be typical of his generation. Right? They grew up in the 1930s. Communism wasn't yet a dirty word. Stalin hadn't done the doctor's trial. We didn't have the pumpkin papers. We didn't have Richard Nixon. The whole communist scare thing hadn't really unfolded yet, and socialism was something people thought about. I think it's like 2 out of 9 members of the New York City Council were communists. Later, that would all go away, as you know. So Coase was a little pinko. And he got his first job working for the Federal Communications Commission as an economist. And they gave him this problem. They said, we have radio frequencies, and we give them out in either big stations, I think they're 50 kilowatt stations, and little stations. I don't remember how big little stations are, 10 or something. Right? So if you went to a city in the 1950s, you'd find the powerhouse radio stations could be heard way, way, way out into the suburbs and even into the next town, and then the little stations could only be heard locally. And you had both types. And they said to him, how many big ones and how many little ones? Go figure this out. And he thought about it, and he thought about it, and he thought about it, and he realized he was never going to answer this question. And he said, why don't we just give the things out in relatively small bundles of frequency and let the radio stations trade it around however they want? And just like your trading game, they will move the frequencies around so they get the right number of big and little stations and the right amount of frequency in terms of what's important to them, which is revenues. And revenues are the same as listeners.